Hello, today we're continuing with our A-level physics revision series, this time looking at telescopes. And I'm going to assume that you've seen or you have knowledge of the material that I covered in the video on geometric optics, the link to which is shown on the screen. But for a bit of quick revision, and again please ignore all the guide marks on the screen, they are there just to make sure I draw a decent diagram. What we showed was that if you take a lens, this is a convex lens, and you have light coming in parallel, which means it will have come from a distance, in theory infinity, that lens will refract the light such that all of that light is refracted to a single point called the focal point. And the distance from the focal point to the lens is called the focal length. We also showed that if you take a lens, and now rather than draw the convex lens, I could draw it like that with the two sides, but in order not to confuse, I'm just going to draw the lens as a straight line. It should look like this, but let's keep it simple and draw it like this. Here is the ray of light that goes straight through and out the other side. And what we said was that if you take an object, then you only need to draw two rays to establish where the image will form. The first ray goes through the lens center and out the other side. The second ray you draw parallel to this line here, and that by definition from here will go through the focal point, and so this now goes through the focal point down through the other side, and where the two lines meet is where the image is formed. And what we said was that the distance from the object to the lens is distance u, the distance of the image to the lens is a distance v, and the focal length is f. And we derived the formula that 1 over f equals 1 over u plus 1 over v. That was all derived in my earlier video. We also showed that if the height of the image is h2 and the height of the object is h1, then the magnification is obviously h2 over h1. In other words, it's the ratio of the image height to the object height. That's the definition of magnification. And we showed that that is equal to v divided by u. That was all shown in the video on geometric optics. Now we're going to consider a two-lens system, and we'll start simply by thinking just of the first lens, which we'll draw here. Again, I'm not going to draw the convex sides to it. But as usual, we take our object, and we only need to draw two rays. The first is the one that goes parallel, and that will go through the focal point. The second is the ray that goes through the center of the lens and out the other side, and where they meet is where you get your image. Now I'm going to draw a third ray, and you'll see why in a moment. This ray goes through the focal point on this side of the lens, and if it goes through the focal point, by definition it will then come out parallel. Right? That ray goes through the focal point, which is here, and anything that goes through the focal point will come out parallel, because if you reverse it, if it comes in parallel, it will go through the focal point. And so we have an image formed here of this object here. But now I'm going to introduce a second lens and see what happens to these light rays. Let's first of all take this light ray here, which goes parallel. Remember, it came along here and it's going parallel. What will happen to that? That will go through the focal point of this lens. We're going to take the second ray, which is this ray that comes down here. It continues, and that is going to be refracted to here. The third ray is the one which leaves the image, goes through the middle of the lens and out the other side to here. And so this image, which is the image of the object from that lens, that image becomes the object of this lens and forms another image here. Now if we look at the two lenses, we can say that if this is lens number 1 and this is lens number 2, then the distance from the object to the first lens we'll call U1, and the distance from the image of this lens to this lens we're going to call V1. Then the distance of this image, which now becomes the object of this lens, to that lens is U2, and the distance from the lens to the final image is V2. And we know that the focal length of this lens is f1, and we know that the focal length of this lens is f2. I am going to call the height of the object h1. I'm going to call the height of the, as it were, the interim image h2. That's the image which is formed from this lens, which becomes the object for this lens. And I'm going to call the height of the final image h3. And obviously we want to know what the magnification is, and the magnification is the ratio of the height of the final image to the original object, which of course is simply h3 divided by h1. But what is that? Well, let's take this triangle here. And what we can say is that the tangent of that angle is h1 divided by u1. And that's the tangent of that angle. But this triangle here has the same angle. And the tangent of that angle is h2 divided by v1. And so the tangent of this angle is h1 over u1. The tangent of this angle here is h2 over v1. And so those two terms are the same. Similarly, I can take this triangle here. And the tangent of that angle is h3 over v2. But that angle is the same as that angle. And the tangent of that angle is h2 over u2. Now, from this equation here, I can write that h2 is equal to h1 v1 over u1. And from this equation here, I can write that h2 equals h3 u2 divided by v2. And since h2 equals this and h2 equals that, that term equals that term. So now I can write h1 v1 over u1 equals h3 u2 over v2. And if I simplify that, I get that h3 over h1, which you'll remember is the magnification that we're looking for, so that's the magnification, equals v1 v2, because it's v1 times v2 comes up here, divided by u1 u2. But v1 over u1 is the magnification of the first lens, and v2 over u2 is the magnification of the second lens. So this is simply equal to the magnification of the first lens multiplied by the magnification of the second lens. So the overall magnification of this arrangement with two lenses, h3 divided by h1, is the overall magnification, and that is equal to the magnification of the first lens multiplied by the magnification of the second lens, as shown in this formula here. Now, a telescope is really just based on the principle of two lenses. Here are the two lenses, but they are arranged in such a way that if you take the first lens and you're looking at objects a long way away, let's say we're looking at the moon or even stars, they're a long way away, the light that comes from them will be parallel. This light will be refracted to a focal point, the focal point of this first lens. But let's suppose we now put this lens such that this distance here is the focal point or the focal length of this lens. What will happen is these light rays will continue, but because they have emerged from the focal point of this lens, they will come out parallel. And now there's a third lens, and that's the lens which is actually in your eye. And that lens focuses the parallel light to a point, the focal point, on your retina, and that sends a signal to your brain such that you can see the picture. So we've got parallel light coming in from, say, the moon. That is refracted to the focal point of this first lens. By placing the second lens such that this distance here is the focal length of the second lens, the light continues and then comes out parallel, and then your eye is very good at seeing parallel light. It's very relaxed, and it can focus that parallel light to a point on the retina so your brain can see it. So we start with parallel light, and after two lenses we end up with parallel light, and you may ask yourself, what on earth was the point of that? The answer, of course, is that you'll end up seeing a bigger image. Let's suppose that this is the size of the moon if you simply look at it with your eye, no telescope. And this is the size of the moon if you look at it through a telescope. In other words, it's bigger, it's been magnified. Let's just draw a line through here, and let's draw a line there. And this is where you're looking at it from. This is the observation point. So when you've got no telescope, the angle from the middle of the moon to the edge of the moon is theta 1. When you have got a telescope, then the angle from the middle of the moon to the top of the moon is theta 2. And you can see that theta 2 is bigger than theta 1. So there has been what's called angular magnification. Now, what is the size of that magnification? Well, the magnification, of course, is always the ratio of the image to the object. So the magnification is the ratio of that distance, which is the width of the full moon as seen through the telescope, to that distance, which is the width of the moon when you're not using a telescope. Now, if we say divide those two by half, or divide them into two, and we'll call that distance B, and we'll call this distance A, then magnification, I think you'll agree, is B over A. But what we can say is that if this distance here is, let's call that just distance D, then we can say that the sine of theta 1 is A over D. Sorry, the tangent of theta 1 is A over D, is tangent theta 1. Similarly, B over D is the tangent of theta 2. So A over D is the tangent of theta 1, B over D is the tangent of theta 2. Now, for very small angles, which is what will be true when we're talking about astronomical observations, the tangent of theta 1 is equal to theta 1 if theta 1 is measured in radians. Similarly, the tangent of theta 2 is theta 2, where theta 2 is measured in radians. And so we have that A over D is theta 1, B over D is theta 2. So rearranging, D is equal to A over theta 1, and D is equal to B over theta 2. Those two are the same, and you can rearrange that to say that B over A is theta 2 over theta 1. But B over A is the magnification. So magnification, angular magnification, is the ratio of the angle of the moon as seen through the telescope, that angle between the centre of the moon and its edge, divided by the centre of the moon and the edge when not seen through the telescope. That is the angular magnification. We've said that light coming from a distant object will arrive, as it were, in parallel. So let's take, this is the moon, here is the telescope. From the, here's the centre of the moon. The light coming from the top of the moon will be coming down to the telescope and essentially in parallel. Similarly, the light coming from the bottom of the moon will be coming as parallel light because it's come from such a long way away. This can't possibly be to scale. This is 250,000 miles away. So you can imagine that once you've got that far away, the angle is going to be very small. That angle there is going to be very small. And the light coming from the top of the moon and the light coming from the bottom of the moon is going to be coming in parallel. So let's now see how a telescope helps us to magnify the moon. Here are our two lenses. Again, I'm not going to draw the convex shape of them. Here is the, as it were, the central line. And here is the light coming from the moon. And you'll notice that it's at a very slight angle. That is the angle, as it were, this is the line that is pointing to the centre of the moon, and this is the line that's coming from the bottom of the moon, and it's coming in at a slight angle. Now what will happen? Well, this light will be refracted down here and out of the other side. This light here will be like this, and it will be refracted, and this light here will be refracted and come out the other side. So as before, we have parallel light coming in and parallel light going out, and of course you can observe that with your eye. And there will have been an image of the moon in between these two lenses, such that this distance here is the focal length of this lens, and this distance here is the focal length of this lens. But why does that help? Well, look at this angle here. This angle is theta 2, and that angle is much greater than this angle, which is theta 1. And remember that the magnification is theta 2 over theta 1. So what is actually happening is that the angle between the centre of the moon and the bottom or the top, as the case may be, has changed and has increased, and so the angular width of the moon is greater, and that means that the moon has been magnified. And that's how an astronomical telescope magnifies what you're looking at. Now remember that this distance from the first lens to the image is the focal length of that lens, and that this distance from the image to the second lens is the focal length of that lens. Now I want you to consider, let's suppose that the height of that image at this point, we'll just call that h. And we'll look at that angle there. And we will say that that angle, of course, is the same as that angle, which is theta 2. So h over f2 is equal to the tangent of theta 2. This is theta 1, and therefore so is that theta 1. And the tangent of this angle is h divided by f1. So h divided by f1 is the tangent of theta 1. Now if theta is very small, which it typically will be, then the tangent of an angle is equal to the angle itself measured in radians. So h over f2 equals theta 2, and h over f1 is theta 1. And so I now can write that h is theta 2 f2, but that also equals theta 1 f1, because h is theta 1 f1, h is theta 2 f2, so these two are the same. So theta 2 over theta 1 which is the magnification, is equal to f1 over f2. And now you've got the famous formula for the magnification of a telescope. The magnification of a telescope is equal to the ratio of the focal length of the first lens divided by the focal length of the second lens. So the larger f1 and the smaller f2, the bigger the magnification. The next question is one of resolution. How far apart do 2 points have to be in order for you to be able to resolve them as two distinct dots? Almost certainly you will all have been able to see those two dots on the screen as two distinctive dots. But if you were to go 100 meters away, you would find that those two dots at some point as you moved away would merge into one, and you wouldn't be able to resolve them as there being two anymore. And what this boils down to is if these are the two dots and this is where you're viewing from, what is the angular separation between the two dots? What does that have to be in order to be able to see those two dots? And here we go back to the principle of the single slit experiment. You remember, if you've got light coming through a single slit, it will form on a screen, here's the screen, it will form fringes. A major fringe in the middle and then smaller fringes on either side. We've covered that in other videos. And this major fringe here is called the airy disk. Now let's suppose you have another object giving off light very close by, such that the interference pattern of that second disk, which I'll draw in pencil, has a airy disk that looks like that. Then you won't be able to resolve the two. They will merge as if they are one. And the argument goes that you can only resolve the two points of light as being distinctive if the airy disk of the second point of light is separate from the first and essentially coincides with the first fringe of the first interference pattern. So the bold line is the fringe pattern for the first point of light, and this is the fringe pattern for the second point of light. And what we're saying is if the airy disk coincides with the first fringe of the bold line, then you will be able to resolve the distances. And the question therefore is, what is the angular separation between that and that? Well, you may remember that we have in fact calculated that. Here is, there is the slit. Here is the light which is going to the first fringe. That's that fringe there. That is the angle. And what we have shown is that if you drop the perpendicular, that is the same angle, that is also theta. And what we showed was that if the wavelength of the light is lambda and the width of the gap is d, then lambda over d is equal to sine theta, where theta is this angle here, the angle to the first fringe. And if that angle is small, and it usually is, then sine theta is equal to theta, where theta is in radians. And so we have the formula that lambda over d equals theta, and what that says is that lambda is the wavelength of the light, d is the size of the aperture, that is, for example, the width of the lens on the telescope, and theta is the angle that you need in order to resolve the two separate points of light. And if your angular separation is smaller than theta, you won't be able to resolve it. If it's bigger, you will. Consequently, if d is large, then theta will go smaller. If d gets larger, theta goes smaller. In other words, the minimum angle that you can resolve becomes smaller, and therefore you can resolve better if you've got a larger aperture for your telescope. So the bigger the aperture, the bigger the lens, then the smaller the angle that you can resolve two distinct points. Two stars in the sky, for example, if they are very close together, can be resolved if d is large enough. That is the width of the lens. Now there is a problem with using lenses for telescopes. One of the major ones is called chromatic aberration. Here I will draw the lens. Here is light coming in from, say, a star or from the moon. And the trouble is, because it's going through a glass lens, it will refract. But as we know, red light and violet light will refract to different extent. So the red light refracts in that way, and the violet light refracts in that way. And so when you are observing, you will actually see the light being split. It's a chromatic split. And since the moon has got a lot of white light reflected from the sun, you will start to see the different colours being separated out because this lens is made of glass. There are other issues. There may be bubbles or impurities in the lens which will cause the image to be distorted. If you have a large lens, and remember you need a large lens if you want to resolve small distances, then the only place you can support it is at the edges, but the lens can become distorted if it's too big. And finally, since f1 over f2, the focal length of the first lens divided by the focal length of the second lens, is the magnification, it follows that you want as big an f1 as possible. You want the first focal length to be as large as possible to get the largest possible magnification, and that means you need a very, very long telescope. These problems can to some extent be overcome if, instead of using a lens, which is what's called a refracting telescope because the light refracts through the lens, you instead use a mirror, which is called a reflecting telescope. And here the light comes in again in parallel, and it is, as we know, reflected to a focal point. I'm not going to actually finish up the line, but it would go to a focal point here. Now, if you insert another mirror at this point, then the light that's on its way to the focal point will now reflect again. And what you do is you have a very small hole. Just make that a hole in the mirror. It won't have a dramatic effect. And the light is then reflected through the hole. So the light comes in here, and then it is reflected again through the small hole to another lens here, such that the light comes out parallel, and then you can observe it with your eye. And that has the same effect as the earlier telescope, but it doesn't have some of the key disadvantages. So you've got parallel light coming in from, say, the moon. It's reflected to the focal point, but before it gets to the focal point, you've inserted another mirror. It's a concave mirror. Both of these are concave mirrors. That concave mirror reflects the light through a small hole in the main mirror, comes out the other side, goes to a lens, which is the eyepiece lens. The light emerges from that lens parallel, because what you make sure is that the image is at the focal point of this lens, comes out parallel, and your eye then focuses the image on the retina. The problem is that that kind of lens, which is called a spherical lens because it is essentially the shape of a sphere, it's just part of a sphere, suffers from what's called spherical aberration. That is to say that the light that comes in parallel is not all reflected to the same point. There is a bit of a hiatus at what should be a single focal point. That's called spherical aberration. And the way you have to get around that is, instead of having a spherical mirror, you need to have a paraboloid or a parabola mirror. You can draw a parabola this way. You take a bar and you take a fixed point, a nail, and you have a piece of string. And you require that the piece of string is absolutely straight, tight rather, and it always has to be coming down here at right angles to this bar. And you put your pencil here. And you make sure that the string is absolutely tight. Remember, it's fixed to this nail and it's fixed to this bar, but it has to come down the bar at right angles. So wherever you move the pencil, if you move the pencil, as long as that string goes straight down and to the nail and is tight, you can have another one here. You can have another one here. If you keep that string tight and you draw with your pencil, what you will find is that the pencil will describe a parabola. And now you can see why a parabolic mirror works, because this is essentially the incoming parallel light from the moon. And it will all be reflected to this point here, which now becomes the focal point. So far we've spoken about light, but you can do the same thing with any form of electromagnetic radiation, in particular radio waves. You can design a radio telescope, which is a massive telescope made out of fine wire. It has an antenna in the middle, and the idea is that the radio waves coming in are reflected off of the parabolic mirror to the antenna, and all of that information is collected. But remember that the resolving angle is equal to the wavelength divided by d, the aperture. Now, D is quite big. It's much bigger than an optical telescope. If you've seen the radio telescope at Jodrell Bank, you'll know that this is quite a big distance. But unfortunately, the wavelength for radio waves is much bigger still. And consequently, the resolving power of a radio telescope is actually quite small, because the wavelength of radio waves is so large that the resolving power of a radio telescope is much, much less than the resolving power of an optical telescope. And the way that the people who do radio astronomy get round this is that they take, this is the Earth. What they do is they put radio telescopes at varying points around the Earth, and essentially that whole area there becomes the value of D in this equation here. So you can actually get much better resolution by having several telescopes all linked together, gathering information. You get a much better resolving power. Plus 1 over V. That was all derived in my earlier video. We also showed that if the height of the image is h2 and the height of the object is h1, then the magnification is obviously h2 over h1. In other words, it's the ratio of the image height to the object height. That's the definition of magnification. And we showed that that is equal to V divided by U. That was all shown in the video on geometric optics. Now we're going to consider a two-lens system, and we'll start simply by thinking just of the first lens, which we'll draw here. Again, I'm not going to draw the convex sides to it. But as usual, we take our object and we only need to draw two rays. The first is the one that goes parallel, and that will go through the focal point. The second is the ray that goes through the centre of the lens and out the other side. Hello, today we're continuing with our A-level physics revision series, this time looking at telescopes. And I'm going to assume that you've seen or you have knowledge of the material that I covered in the video on geometric optics, the link to which is shown on the screen. But for a bit of quick revision, and again please ignore all the guide marks on the screen, they are there just to make sure I draw a decent diagram. What we showed was that if you take a lens, this is a convex lens, and you have light coming in parallel, which means it will have come from a distance, in theory infinity, that lens will refract the light such that all of that light is refracted to a single point called the focal point. And the distance from the focal point to the lens is called the focal length. We also showed that if you take a lens, and now rather than draw the convex lens, I could draw it like that with the two sides, but in order not to confuse, I'm just going to draw the lens as a straight line. It should look like it continues, and that is going to be refracted to here. The third ray is the one which leaves the image, goes through the middle of the lens and out the other side to here. And so this image, which is the image of the object from that lens, that image becomes the object of this lens and forms another image here. Now if we look at the two lenses, we can say that if this is lens number 1 and this is lens number 2, then the distance from the object to the first lens we'll call U1, and the distance from of the image of this lens to this lens we're going to call V1. Then the distance of this image, which now becomes the object of this lens, to that lens is U2, and the distance from the lens to the final image is V2. And we know that the focal length of